In a 45-degree desert with zero natural rivers, turning a tap in Dubai feels completely automatic. It is a simple action, but behind that ordinary glass of water is an invisible industrial chain. This is a city surrounded by salt water and burning sand. To make water flow from the tap, Dubai relies on power stations, desalination equipment, high-pressure pumps, reservoirs, and a vast underground pipeline network. If you look closely at that system, a new question emerges. One broken machine would not make Dubai run dry. So, what would? Where does this fresh water really come from, and why is every single drop permanently tied to the electricity grid? To answer that, we have to understand how many layers of protection would have to fail before that glass of water becomes empty, and this multi-billion-dollar oasis is forced to surrender to the desert. The story of Dubai's water does not begin with an aquifer. It begins at the coastline of the Arabian Gulf. In this climate, fresh water is not something the city simply finds and collects. It is something that first has to be manufactured. Dubai transforms seawater into a highly controlled industrial product. This transformation requires massive coastal facilities that pull in ocean water and push it through intensive filtration and separation processes. The scale of this operation is difficult to comprehend from the center of the city. Millions of gallons of seawater are continuously drawn into intake structures, treated, and converted into potable water every single day. In Dubai, water is not merely a natural resource that the city receives. Much of it has to be actively produced through an industrial process known as desalination. But a factory cannot operate on its own. Manufacturing anything requires raw materials and a power source. When water becomes an industrial product, the process of making it suddenly inherits all the vulnerabilities of heavy manufacturing. The plants separating salt from seawater need a constant, immense input of energy to keep running. The raw material is infinite, but extracting the salt is heavily constrained by engineering limits. So what exactly does a water factory need to keep operating without interruption? The answer is a permanent supply of electricity. Dubai's water system has an entire energy system operating directly behind it. Historically, the city relied heavily on traditional thermal desalination. That older method was deeply integrated with power production, using heat from electricity generation to boil and condense seawater. Today, Dubai is increasingly expanding its use of seawater reverse osmosis. The city's electricity and water authority is driving this shift because reverse osmosis requires significantly less energy and helps decouple water production from conventional power generation. But decoupling does not mean water is completely free from the power grid. Reverse osmosis still demands an enormous amount of electricity to function. The process relies on massive electric pumps to force seawater through microscopic membranes at extreme pressure. It requires power for intake systems, chemical pretreatment, and digital network controls. Even with modern efficiency, the basic physics of pushing salt out of water requires continuous electrical force. Dubai does not merely need electricity and water as two separate utilities. Electricity is an active part of the machinery used to secure fresh water. Without a reliable flow of electrons, the flow of water stops at the plant. This creates a strict physical dependency between the power grid and the city's taps. Cooling systems and drinking water are competing for the exact same resource. And recently, both sides of that relationship hit unprecedented levels of pressure at the exact same time. In the third quarter of 2025, the Emirate recorded a massive surge in utility consumption. The Electricity and Water Authority reported that peak power demand reached approximately 11.4 gigawatts. At that time, this was a record high for the electricity system. But the pressure was not isolated to the power grid. The water infrastructure was also experiencing unprecedented demand. Peak daily desalinated water demand hit a record 487 million imperial gallons. These two records colliding in the same quarter reveals the true nature of Dubai's infrastructure challenge. Extreme summer heat often drives the narrative, but heat alone did not cause these numbers. The baseline demand is continuously pushed higher by population growth, rapid urban development, and expanding economic activity. When summer arrives, the extreme ambient temperature acts as a severe pressure multiplier. Millions of air conditioning units work harder to reject heat, drawing massive amounts of power. At the exact same time, water consumption rises across residential, commercial, and hospitality sectors. The electricity system must handle the cooling load while simultaneously powering the desalination plants that are running at peak output to meet the water load. The dual surge puts both networks under heavy operational stress. The turbines are generating maximum output, and the pumps are pushing maximum volume. And within that quarterly report, the water side contained one specific number that looked far more uncomfortable than the rest. At the end of that same quarter, the authority reported Dubai's total installed desalinated water production capacity. The system was rated for 495 million imperial gallons per day. Compare that to the peak daily demand of 487 million imperial gallons. On paper, the gap between the maximum installed capacity and the peak consumption appeared incredibly narrow. Looking at those two numbers side by side, it is very easy to jump to a catastrophic conclusion. But this does not mean Dubai was only 8 million gallons away from running completely dry. Installed capacity is not a simple countdown meter or a fuel gauge. Operating conditions, daily fluctuations, and system management play a massive role in how water is actually dispatched. The city does not consume peak demand every single second of the day. Furthermore, total production capacity is balanced alongside storage reserves and operational buffers that absorb sudden spikes in consumption. Treating the numbers as an immediate crisis fundamentally misunderstands how heavy infrastructure is managed. However, the closeness of those figures still highlighted a very real engineering reality. The operational limit was visible, and the city knew it had to build ahead of the curve. The margin was tight enough to prove that continuous expansion is an absolute necessity. If this was not an 8 million gallon countdown to disaster, why was Dubai already rushing to add significantly more production capacity? The answer was already being built on the coastline. In the first quarter of 2026, Dubai commissioned Block A of the Hassian seawater reverse osmosis plant. This massive new facility added 60 million imperial gallons per day to the network. With that single expansion, total installed desalination capacity immediately jumped to 555 million imperial gallons per day. The authority also confirmed that additional capacity was expected to come online throughout the rest of the year. Dubai identified its growing requirements and engineered a massive capacity upgrade to handle them. The pressure from the previous year was relieved by pouring concrete and installing more advanced membrane technology. It seems like the perfect technological victory over a harsh environment. The physical gap between production and consumption widened, giving the city room to breathe. But the underlying reality is slightly more complicated. The new infrastructure at Hassian is highly efficient, but it still relies entirely on electric pumping, intensive pressure management, and digital controls. Dubai widened the water system, but it did not remove energy from the water equation. Expanding production simply means building a larger factory that requires a continuous flow of power. Every time Dubai removes one capacity constraint, another infrastructure dependency appears directly behind it. The more water the city produces, the more energy it must dedicate to moving it. And securing the raw production of fresh water is only the first step in keeping the tap running. Producing potable water is only half the engineering equation. Once the fresh water leaves the boundary of the plant, it still has to physically reach the consumer across an enormous urban footprint. That requires pushing the water through a vast network of transmission pipelines, massive pumping stations, and highly pressurized local distribution grids. The Electricity and Water Authority manages this continuous flow using advanced digital monitoring and supervisory control systems. Thousands of sensors track flow rates, pressure levels, and water quality across the entire transmission network in real time. These digital controls ensure that the water manufactured on the coast makes it to high-rise apartments miles inland without losing pressure. But this sophisticated distribution web reveals another critical reality about the infrastructure chain. A desalination plant can operate with absolute perfection on the coast. If the pumps, control valves, or building systems downstream suddenly stop doing their job, the customer turning the tap receives nothing. The physical distance between the production facility and the residential glass of water is filled with mechanical dependencies. Every mile of pipe and every neighborhood booster pump is another potential point of friction. The answer lies in how engineers intercept the water before it reaches the end user. So if production and consumption are constantly fluctuating and network equipment requires routine maintenance, what keeps a short mechanical disruption from immediately reaching the tap? The first layer of protection Dubai buys is physical storage. Across the emirate, massive concrete reservoirs are strategically positioned to absorb the daily mismatch between how fast water is produced and how fast it is consumed. Take the Nkali Reservoir as a prime example of this protective strategy. This facility is connected to the city's network with a storage capacity of 120 million imperial gallons. The government describes these facilities as vital components for increasing storage volume, maintaining water flow, and ensuring total network reliability. When daily demand spikes or a production unit temporarily powers down for maintenance, these reservoirs feed the network, ensuring the pressure at the tap remains absolutely constant. A reservoir in this story is not merely storing a liquid resource. It is fundamentally storing time. It creates a physical buffer that allows engineers to manage short-term disruptions without the end user ever noticing a drop in pressure. It smooths out the peaks and valleys of daily urban life. But even the largest concrete tanks have strict physical limits. A standard surface reservoir is designed to manage daily operational fluctuations, not prolonged emergencies. If a severe incident cut off production for an extended period, surface storage alone would eventually deplete. To handle a massive disruption, Dubai had to design a reserve system on an entirely different scale. The city started hiding water deep under the desert. Instead of relying solely on surface tanks, Dubai developed an aquifer storage and recovery system hidden beneath the sand. During periods of lower consumption, excess desalinated water is injected deep into subterranean rock formations. The water is securely held in the geological layers, turning the natural desert itself into a massive, invisible vault. When emergency conditions arise, the water can be pumped back to the surface, treated, and returned directly to the distribution network. Official government materials describe the full-scale design of this strategic reserve as capable of storing up to 6 billion imperial gallons. Under that planned capacity, the system is designed to provide more than 50 million imperial gallons per day for 90 consecutive days during severe emergencies. This changes the entire calculus of urban survival in a desert climate. Why does a city build an emergency water buffer measured in months rather than hours? Because the government clearly understands the exact nature of the manufacturing chain. They know that heavy industry is never perfectly immune to extreme disruption. The scale of the underground reserve reflects the magnitude of the potential risk. By engineering a system to hold billions of gallons underground, Dubai is actively creating distance between a severe infrastructure disruption and a citywide crisis. It is the ultimate insurance policy against the vulnerabilities of coastal production. When you view the entire architecture from a high vantage point, the system appears almost completely invulnerable. The city has steadily expanded its highly efficient seawater reverse osmosis capacity to meet rising demand. It operates massive surface reservoirs that constantly balance daily consumption and guarantee immediate pressure. It has engineered a strategic underground reserve designed to sustain the population for 3 months under emergency conditions. And all of this is actively managed by a digital control network monitoring the flow at every single stage of distribution. This is not a fragile utility network waiting for one hot summer afternoon to destroy it. Dubai has deliberately built aggressive redundancy, massive storage, and advanced operational intelligence into the very foundation of the city. Official infrastructure descriptions continually emphasize water security, reliability, massive reserves, and emergency access. The engineering margins have been calculated, funded, and built into the physical environment. The safety nets are real, and they are embedded into the urban grid. For a brief moment, this looks like a total engineering victory over a harsh environment. It feels as though the city has permanently solved the problem of water scarcity. But look closely at exactly what it took to make the system this resilient. When you trace the engineering backwards from the tap, a very specific pattern emerges across the entire emirate. Freshwater scarcity forced the creation of massive coastal desalination plants. The extreme energy intensity of older thermal desalination pushed the transition to more efficient seawater reverse osmosis. The physical mismatch between daily production and hourly consumption required the construction of massive surface reservoirs. The threat of a severe emergency disruption led to the design of strategic underground aquifers hidden beneath the sand. And the operational uncertainty of a vast distribution network made continuous digital monitoring an absolute necessity. Dubai did not remove the desert from the equation. It built aggressive layers of heavy infrastructure between the desert and the tap. But the sheer scale of that resilience is exactly what exposes the true nature of the vulnerability. Every time engineers add a protective layer to secure the water supply, they are simultaneously adding another mechanical system that must continue to operate correctly. A massive pumping station protects the distribution pressure, but only as long as it has electricity. A smart monitoring grid protects the flow, but only as long as the digital infrastructure remains online. The backup systems have their own dependencies, and those dependencies require continuous power. This brings us back to the mystery we opened with at the very beginning. If the city is this heavily defended, what would actually have to fail before the glass of water became a severe problem? To answer that, we have to look at what the system is explicitly designed to survive on a daily basis. Imagine a hypothetical scenario where one major desalination unit suddenly becomes unavailable during the peak summer months. In a system this wide, a single offline unit is highly unlikely to instantly empty the city's pipes. Other active production facilities, combined with millions of gallons of stored water, would immediately compensate for the lost output. If a short-term production disruption occurs, the surface reservoirs and intelligent system management step in to absorb the shock without dropping the pressure. If a localized distribution problem strikes a specific neighborhood, engineers can isolate that section of the network and reroute the flow while repairs are made. Dubai's water infrastructure is designed precisely so that one isolated equipment failure does not automatically become a citywide water crisis. The safety nets are robust enough to catch single points of failure before they reach the consumer. Therefore, asking which single machine could break is the wrong way to look at the threat. A lone mechanical fault is simply an engineering problem with an established protocol. The danger requires a sequence of events that overwhelms the built-in redundancy. The real question is fundamentally different. How many layers would have to fail faster than the system could mathematically compensate? This is the scenario where the safety nets stop looking like guarantees and start looking like a countdown. If a prolonged electricity disruption were to strike the region, it would instantly constrain parts of the infrastructure chain. Without maximum power, a portion of the total desalination output would become unavailable. To make up for the missing production, the surface reservoirs would begin absorbing the mismatch, draining their stored volume to keep the pressure stable. As those surface tanks deplete, the strategic underground reserve would be activated, pumping its emergency buffering to buy the city more time. But that stored water still needs intact electrical pumping and transmission infrastructure to physically reach the customers. If those downstream systems are also constrained by the original power disruption, the physical storage volume starts to matter much less. You can have billions of gallons sitting in a vault, but without the energy to move it, the water remains trapped. Now, the system approaches something fundamentally different from an isolated incident. Extreme heat is simply the baseline pressure. One equipment failure is an operational incident. A prolonged failure cascade, cutting across power generation, active water production, and mechanical distribution, is the real collapse scenario. If protections were exhausted faster than recovery occurred, the sheer weight of the climate would break through the engineering. Every backup system that initially made Dubai appear almost invulnerable now reveals the exact opposite. It shows exactly how many invisible systems must remain perfectly operational just to make water look effortless. Look back at the original faucet. Look at the glass of water filling in a residential kitchen. Look at the skyline burning under 45 degrees Celsius heat. At the beginning of this story, turning that tap simply felt like an automatic human right. Water simply appears. But now, that ordinary glass of water means something entirely different. It is the final output of a continuously operating, heavily industrialized, and highly vulnerable infrastructure chain. Dubai's true vulnerability is not simply that it exists in an arid, unforgiving climate. It is that ordinary freshwater has permanently become the product of heavy machinery. Every drop you drink requires a turbine spinning on the coast. Every drop requires high-pressure pumps fighting the physics of the ocean. And as the population expands and the skyline grows denser, every single invisible system behind that tap becomes increasingly important. The distance between the desert and the tap is entirely synthetic. If the energy stops flowing, the mechanical distance collapses, and the desert reclaims the space. Dubai didn't eliminate water scarcity. It simply engineered an incredible amount of mechanical distance between absolute scarcity and the tap. The city built a massive machine to keep the reality of the climate at bay. But machines require power, maintenance, and constant supervision. In a desert megacity, which would concern you more? Losing electricity first, or losing the fragile water infrastructure that electricity helps sustain? This documentary is for educational and analytical purposes only, based on available data and reported operational capacities. It does not constitute professional engineering, financial, or civic planning advice. System conditions and capacity can change rapidly. If you want to understand the invisible infrastructure keeping modern megacities alive, hit subscribe and share your thoughts in the comments below.